All right, so let's talk about regioselectivity, because so far the examples I've shown you, the generic mechanism and the addition of HCl, have been to what's called a symmetrical alkene. It was the same on both sides of the double bond. What happens if it's not? What happens if you have an unsymmetrical alkene, such as maybe this one, for example? What happens then? Well, that's when a rule called Markovnikov's rule comes in. Markovnikov's rule states the addition of a proton to a double bond of an alkene results in the product with the acidic proton bonded to the carbon atom that already holds the greater number of hydrogens. That's Markovnikov's rule. So in other words, let's just do this again. Alkene results in a product with the acidic proton, this one right here, bonded to the carbon atom that already holds the greater number of hydrogens. So this carbon holds more hydrogens than that one does. So according to Markovnikov's rule, this hydrogen should go to this carbon. And that's true. That's where it's going to go. Additionally, in an electrophilic addition of the alkane, the electrophile adds in such a way that it generates the most stable intermediate. Now, this is the one I want you to circle, highlight, and otherwise make a big deal about, because this is the rule that I really want you to focus on. Now, the first rule I read you is right. It's correct. This rule is a restatement of it. Now, the first rule I read you, or the first Markovnikov rule I read you, was dealing with the protons, was thinking about the reaction from the proton's point of view. Now I want you to think, and this is how every chemist thinks, think about the think about the intermediate stability. The intermediate stability. Stable intermediates always form the fastest. So if you can, the stable intermediate will be the predominant, if not the only intermediate in a reaction. So let's see an example of Markovnikov's rule in play. So here we have our example of an unsymmetrical alkene. We're going to add HCl across that bond. And I'll tell you right now, the product is going to be this. And I'll just draw the corresponding potential product. This one is not formed. So let's draw a big purple X through it. That one is not formed. Now that's interesting. We get complete selectivity for one over the other. We get this one, but not this one. Let me draw that chloride a little better. It's kind of invisible up there. There we go. So this one forms. This one does not. Let's see why. Well, whenever you have a question like this where it's like, why doesn't this happen? Or why do we get this but not that? Always, always, always go to mechanism. It may not be right, but at 95% of the time is the right thing to do. Go to mechanism. So now, we have to decide. We have a choice here. We have a choice here. We can either put the hydrogen to the right of the double bond or to the left. The hydrogen can either go here or it can go here. And I say to students, when you're first learning, draw both. When you're first learning, draw both. That way you don't make any silly mistakes. So let's draw both. Let's put the hydrogen on the right carbon and see what the intermediate looks like. I will put a plus charge here, and let's put the hydrogen on the left carbon and see what we think. I will put a plus charge here. Well, now, if you think back to your stability of carbocations, you will all agree with me that this is tertiary and this is primary. And you guys will all agree with me, if you think back to your stability of carbocations, that this is not as stable as this. Tertiary cations are more stable than primary. So this one is not the one we want to deal with. The one we want to deal with is this one. And the chloride will attack that carbon right there and give us the desired, or the, I don't know if it's desired, but maybe it's a desired product. Give us the product of the reaction. So yes, this reaction is most definitely following Markovnikov's rule, but better to say it like this. It's giving me the most stable carbocation, which is then attacked by the nucleophile. All right, so there's the, oh my goodness, I'm sorry. There we go, that's better. Let's fix that up. There we go, giving you the observed product right there. So that's the mechanism you draw to make that. Let's see another example, because it's always good to do a few examples of these questions, especially for students who are just learning the chemistry. Let's put it into a ring. Now another way these questions are asked is predict the product. So I might give you this on an exam and say, you tell me what the product is. Don't let that phase you. Same idea. Mechanism. Use mechanism to help predict the product. So let's start here. And let's do HCl. Let's do that in blue. Oops, sorry. Let's do that in black and green. And now the pi bond will attack the hydrogen. And the bond electrons go to the chloride to form an ion of chloride. And let's draw some arrows to the right here. So that's going to give us this carbocation. And that'll put the black hydrogen down here, because that will generate the tertiary carbocation. Now, let's draw the other potential carbocation so we can see why I picked this one. So instead of going to instead of putting the hydrogen on the bottom carbon, let's mix things up and put it on the bottom carbon, or the top carbon, excuse me. So all I'm going to do here is I'm going to draw both potential intermediates. So the same mechanism, this arrow attacks that hydrogen, bond electrons go to the chlorine to form chloride. I could have had this, where I put the hydrogen on the bottom, or this one, where I put the hydrogen on top. Putting it on the bottom gave me a tertiary carbocation. Putting it on the top gave me a secondary carbocation. Everyone I think will agree that that one probably doesn't form. Tertiary is definitely more stable, so it's going to be the one that forms in preference. And now the chloride will attack it. The chloride will never attack this because this never forms. And that is the expected product of this reaction. And this is most definitely the Markovnikov product. It follows Markovnikov's rules.